So in the previous video, we saw that we could use polar coordinates to evaluate many of these double integrals, especially if we were integrating over what's called a polar rectangle. And while these polar rectangles do come up in a lot of different problems, it's useful a lot of the time to integrate over slightly more general regions where we can also use polar coordinates. So we're going to look at what that would mean to integrate over a general polar region. Now, the kind of polar region we're going to look at is a region that's bounded by the graphs of two functions of the form r equals f of theta. So the radius is a function of theta. So this is kind of similar to the type 1 and type 2 integrals that we did in rectangular coordinates. So if you remember, we had the type 1 integral was the region between two graphs that were functions of x. The type 2 integral was between two graphs that were functions of y. And here we're saying we're just going to look at the region that's between two graphs where the radius is a function of theta. So let me sketch for you what one of these general regions look like, and then we'll go over how we're going to set this up. So this is the type of region we're looking at here. So what we have here is a coordinate system, and we've got two lines that are representing constant theta measurements. So an angle measure theta equals alpha, and then an angle measure theta equals beta, and those are going to be bounding in the radial direction. And then we've got these two graphs which are functions of theta, r equals, say, h1 of theta, r equals h2 of theta. So the radius is a function of theta, and it's just saying between theta equals alpha to beta, it's just the region between the graphs of those two functions. So that blue region right there. So if we wanted to write down symbolically what this region is, we could write it like this. So it consists of all the points with polar coordinates r theta, where theta is between alpha and beta, and r is between h1 of theta and h2 of theta. Now, how is this going to be set up if we're going to integrate a double integral over this region? Well, it's going to be very similar to the polar rectangle that we did before. The only difference is, instead of having constant values for the radius, we're going to have these functions of theta. In other words, it's very similar to a type 1 or type 2 region in rectangular coordinates. So this is the expression that we get. So if we want to find the double integral over d of any function f of xy dA, so we're going to do an iterated integral, so the integral from alpha to beta, of the integral from r equals h1 of theta up to h2 of theta, and then we have to integrate f of r cosine theta, r sine theta. So this is just saying what we were doing before with the polar rectangles. Wherever you see x, you have to substitute r cosine theta. Wherever you see y, you have to substitute r sine theta. And then we have dr d theta, and as before, don't forget to include the r because it's polar coordinates. So we have to include the r dr d theta. Now, what we can do to kind of do a quick gut check on this to see if it seems right is we know from Calculus 2 we did areas using polar coordinates. And so we can kind of check this out by integrating the function 1 and seeing what formula we get for the area here and see if that matches up with what we've got from Calc 2 before. So let's go ahead and do that. So let's look at integrating 1 over this region. So the area of D is equal to the double integral of 1 dA. And by the above formula, this is the integral from alpha to beta, integral from h1 theta to h2 theta of r dr d theta. Now the integral of r, of course, is r squared over 2. So we're going to evaluate r squared over 2 between h1 and h2. And I'm going to take out the factor of 1/2, and what we're going to get is 1/2, the integral from alpha to beta of h2 of theta squared minus h1 of theta squared. Now, why is this the same area that we would get if we used Calculus 2 formula? Well, if you remember from Calculus 2, the formula for the area that we got was 1/2 the integral from alpha to beta of r squared. So where r is a function of theta. So all we're doing here is this is just saying the difference between the two. So you're going to take the area that's this kind of sector region out to H2, and then you're going to subtract off the sector region out to H1. So you just get the difference between the two. You get 1/2 the integral of H2 squared minus 1/2 the integral of H1 squared. That's what you get from Calc 2. And what we see here is if we break up this integral then into the two pieces, so if we break it up into two integrals, that's exactly what we get here. So it does end up agreeing with the formula that we got from Calc 2. Okay, so we're going to look at a couple examples. The first example is going to be a volume. So we're going to calculate the volume of a solid region. And we could do this in rectangular coordinates, but in polar coordinates, the calculations are going to be much better. So that's the reason we're using polar coordinates. And the second problem, we're going to be finding an average value of a function. And there's a couple reasons we're using it. So not only is the integrand easier in polar coordinates, but the region itself is going to be defined kind of as a polar region. So it's going to be defined in terms of polar coordinates. So to try and redefine the region in terms of rectangular coordinates would actually be making it much more complicated. If it's already given to you in polar coordinates, just use polar coordinates. So let's look at the first problem here. So this says we want to find the volume of the solid region bounded above by this paraboloid 4 minus x squared minus y squared, bounded below by the xy plane, so z equals 0, and inside the cylinder. So we need to kind of get a picture of what's going on here. So I'm going to draw a little picture, and then I think I'm going to go to the CalcPlot 3D to give you a picture as well, just because my drawing abilities are not the best. But I think I can get a pretty accurate drawing here. So give me a second, and I'll sketch the graph. Okay, so you can see this is a paraboloid that opens down. So it's got its highest point is at 4, and it opens down. And then, so we're looking everything above the xy plane and below this. Now, normally this would be just a double integral we could set up easily in polar coordinates because it would be just over, the disk of radius 2 centered at the origin. But it also says inside this cylinder. Now, this cylinder, if the intersection of that cylinder with the xy plane is entirely within that disk of radius 2 in the xy plane. So it's actually a much smaller region, so I kind of shaded it in blue here. So it's everything underneath that paraboloid, but also inside this kind of cylinder. It's almost like you take the cylinder and you kind of, cut it like you would cut dough. You have a cutter that goes through it. So let's look in CalcPlot 3D, and it's probably be a little bit better picture. All right, so 4 minus x squared minus y squared. Okay, let's back up a little bit. Okay, so there's our paraboloid. And of course we've got, change that, there we go. And we've got the xy plane, so I'm just going to do, z is equal to 0. Okay, so there's the plane. And also inside, inside that cylinder. Okay. So that cylinder was, now I'm going to do this as an implicit surface. Okay, so the implicit surface was x squared plus y squared is equal to 2y. All right, there it is. Okay, so if we go over here and look now, you can see. Okay. So if we look down on it here, you can see that it's everything below that paraboloid, above the xy plane, and inside there. So you can't really see the region here. It's kind of out of view because it's on the other side of the paraboloid. But you can, if I make it transparent, so you can kind of see inside there. So just imagine what that region looks like inside there. So what we're going to have to do is integrate over this over this cylinder. So integrate over the circle that it intersects in the xy plane, and then we're going to have to integrate the 4 minus x squared minus y squared. So this is going to be set up for polar coordinates well because the cylinder is given by x squared plus y squared equals 2y. So there's, whenever you see x squared plus y squared, or even just x squareds and y squareds, polar coordinates should come to mind. And then, of course, the paraboloid is 4 minus x squared minus y squared. So the first thing we need to do is figure out what's the polar coordinates for this cylinder. That's the main thing, because the paraboloid, it's clearly 4 minus r squared, but it might not be quite as obvious what it is for this circle. And if you don't remember polar graphs, so you don't remember graphing in polar coordinates, it's easy not to remember what this looks like, but we can get it by using the substitutions. Okay, so the cylinder is given by x squared plus y squared is equal to 2y. So that means r squared is equal to 2 times y is r sine theta, which means if I subtract this, it's going to be r squared minus 2r sine theta is equal to 0. Now I can factor out an r. R times r minus 2 sine theta is equal to 0, which means either r equals 0 or r is equal to 2 sine theta. Now, r equals 0, that's just going to be the origin. So really, we're not so much interested in that. What we're really interested in is the r equals 2 sine theta. So that ends up being the polar equation for this circle. It's a circle. Well, here, let's go ahead and actually let's complete the square and see what this is in rectangular coordinates. We can find the center and the radius. So if we subtract 2y, we've got x squared plus y squared minus 2y, and then we want to add 1 is equal to 1. Okay, so x squared plus y squared minus 2y plus 1 equals 1, so that's x squared plus y minus 1 squared is equal to 1. So this ends up being a circle with center at 0, 1, and radius equal to 1. Let me move this down a little bit. Okay. So let's look at the intersection in the xy plane of both the cylinder and the paraboloid, how those intersect in the xy plane. So there's the circle of center 0, 1, radius 1, and then the intersection in the xy plane of the paraboloid is going to be the circle centered at the origin with radius 2, so that's going to look like this. Okay, so roughly like that. Anyway, it hits it here at 2. Hits it here at negative 2. This goes out to negative 2. And so on. Now, let's just check, what does our theta have to run between here? So when theta is equal to 0, so this is for the inner circle here, r is equal to 0. When theta is equal to, let's say, pi over 4, well, sine of pi over 4 is root 2 over 2, so that means r is going to be equal to root 2. So that means it's going to go through that point right there, 1, 1. When theta is equal to, say, pi over 3, so now the sine of pi over 3 is going to be root 3 over 2, so that means r is going to be root 3. So it's going to look something like this. Okay, so there you can see these are all theta values. And then when you get to pi over 2, sine of pi over 2 is 1, so r is equal to 2. So that just means you go straight up the y-axis at pi over 2. And then this is going to continue. You can see how this kind of continues all the way over till you get to, finally, theta is equal to pi. Then that means that r is equal to back to 0. So it increases from 0 up to 2, back down to 0, from 0 to pi. So the point is, the reason I'm going through this is, it's a real common mistake to set this up, the interval of integration to go from 0 to 2 pi. You think, well, it's a circle. I have to go around the whole circle. That's 0 to 2 pi. No. What you really get for this is just from 0 to pi. So let me put in maybe one more. So notice this here. That's actually, right, 3 pi over 4. So you really only have to go from 0 to pi. So that's going to be our theta limits. So theta is going to go from 0 to pi. R is going to go from 0 to 2 sine theta. And that's how we're going to set up this double integral. All right, so let's start the calculation. So we're integrating over this region, d, the 4 minus x squared minus y squared dA, and we just said that was from 0 to pi, 0 to 2 sine theta, 4 minus r squared, and then don't forget your other r, so the r, dr d theta. So this is going to end up being 4r minus r cubed, and we're going to have to integrate that with respect to r. And when we integrate this, so this is going to integrate to, let's see, 2r squared minus r to the 4th over 4. And it looks kind of intimidating, but remember the 0 is going to go away. And the 2 sine theta, we're going to get a sine squared, we're going to get a sine to the 4th. So those are even powers of sine, so we have to use some of the trig identities to reduce the power. So I'll go over this on the side when we get to it, but it's going to be doable. It's a little tricky. You have to remember your trig identities from Calc 2, but we can do it. Okay, so we're going to be evaluating that, and of course it's 0. That doesn't contribute anything. So let's see what this gives us. So I'm going to move this down. How much more room do we have? I think we have enough room. Okay, so this is going to be the integral from 0 to pi. Now we've got 2 sine theta all squared would be 4 sine squared, but there's another factor of 2, so that's 8 sine squared. Subtract 2 sine theta all to the 4th would be 16 sine to the 4th, but it's over 4, so it's only 4 sine to the 4th. Okay, and it's all of this d theta. Now, the sine squared, so let's remember our trig identities here. Sine squared is 1 minus cosine 2 theta over 2. But the sine to the 4th, I think we should do a little calculation on the side. So I'm going to go ahead and do that, and then I'll just pause the video and write it out, and then we'll come back to it, and I'll talk through it. It's just some tedious algebra stuff. Okay. So sine to the 4th, well, that's sine squared squared. We just said that sine squared was 1 minus cosine 2 theta over 2. So we have to square that. So if we multiply that out, so 1 minus 2 cosine 2 theta plus cosine squared 2 theta over 4, and then we're going to apply the identity again to cosine squared. It's 1 plus cosine 2 times 2 theta, so it's 1 plus cosine 4 theta over 2. And so this is what we end up getting down here. So that's what we're going to have to do. We're going to have to do minus 4 times all of this. So this is just kind of tedious. So let's see here. We've got the integral from 0 to pi. So it's going to be 8 times 1 minus cosine 2 theta all over 2 minus 4 times, so now I have to copy everything that's over here, 1/4 minus 1/2 cosine 2 theta plus 1/8. I'm going to go ahead and distribute the 1/8. So plus 1/8 plus 1/8 cosine, just need a little bit more room. Give me a sec. 4 theta, I love that I can do that. 4 theta d theta. Okay, so all of this d theta. Okay, so that's going to be, just clean this up a bit. All right, so that's 4. If I distribute the 4, actually let's add the 1/4 and 1/8 is going to make 3/8. All right, great. So we got 4 minus 4 cosine 2 theta. Now I need to distribute the minus 4. Okay, so if I distribute over the 3/8, that's going to give me minus 12/8, which is going to be minus 3/2. Minus 3/2. Plus 2 cosine 2 theta. And then across the 1/8 cosine 4 theta, that's minus 1/2 cosine 4 theta. All right. And let's see, there's still a couple terms I can combine here. It's not going to really matter because, as we'll see, these are going to end up evaluating to 0 in any case, but this ends up being minus 2. So the minus 4 and the plus 2 makes a minus 2. So that's a minus. All right, now we can go ahead and integrate. 4 minus 3/2. Okay, 4 minus 3/2 is 5/2. So that's going to integrate to 5 theta over 2. And then, let's see, minus 2 sine 2 theta over 2. So that's just minus sine 2 theta. And then the cosine 4 theta, it's going to be sine 4 theta over 4. So minus 1/8 sine 4 theta. And this is all between 0 and pi. Now, at 0, these are all going to evaluate to 0. So we can cross that out. However, at pi, sine of 2 pi and sine of 4 pi, since those are integer multiples of pi, those are also 0. So really, this just works out to evaluating 5 theta over 2 at pi. So this is 5 pi over 2. So the volume of this solid region is 5 pi over 2. Okay, so I think that's a good illustration of using polar coordinates to evaluate something that's given in rectangular coordinates, that it's easier in polar coordinates. The next one we're going to use polar coordinates because the region itself is going to be given in polar coordinates. So this problem says find the average squared distance from the origin of a point in the region, and the region is the region in the first and fourth quadrants outside the unit circle and inside the lemniscate r squared equals 2 cosine 2 theta. So we need to stop and think about a few things here. So first of all, average squared distance. So we need to know how to interpret that. So the distance from the origin in polar coordinates would be r. So they want the squared distance from the origin. So that's going to be r squared. So that's suggesting we're going to integrate r squared over this region. But it says average. So what that's saying is they want the average value of the squared distance. So it's not just going to be the double integral of r squared. We're going to have to divide that by the area of the region. So we're going to have to find two double integrals here. The first one, that's going to be the double integral of r squared. And then we're going to have to divide that by the double integral of 1. So we're going to have to find the area. Now, it's going to be the same limits because it's the same region, but we're going to have to do the double integral twice. The second thing is we have to graph what these two graphs look like so we can figure out first what the region looks like and then how we're going to set up the limits. We don't know, theta should go from what to what. It's not clear till you look at a picture of what's going on. So let's start off by, let's graph what the region is going to look like and see if we can come up with the limits. So we can start off with the unit circle, but let's see, what does this lemniscate look like? So I'm going to run through some values of theta over here, and let's see what we get. So first of all, we're looking at r is equal to square root of 2 cosine 2 theta. Now, yeah, it's plus or minus square root, but what we're going to see is the minus just runs through the same graph. So for now, let's just look at positive square root 2 cosine 2 theta. Now, remember here, when we're doing this, we can't have a negative under the square root. So any values of the cosine that give us a negative, we could kind of graph in dashed line, but remember that that's not going to be part of the graph. And again, this is all stuff that is gone over in pre-calc and Calc 2, so if you want to go back and review, I put up some videos about polar graphs, and you can go back and watch that where they go over the different graphs in polar coordinates. Now, so let's start with, say, theta equals 0, and let's go through pi over 4, pi over 2, theta equals pi over 2, pi over 4, and let's just see what we get here. So when theta is 0, so cosine of 0 is 1, so we're going to get r is equal to root 2. Whoops, I got these out of order. Should be pi over 4 first and then pi over 2. There we go. So at pi over 4, now we get cosine of pi over 2, which is 0. So already we've decreased down to 0. At pi over 2, we get a negative number because it's cosine of pi, which is negative 1. So that doesn't factor into it. So what's happening is the radius starts at root 2, which is about here. And as we get up to pi over 4, it's already, so here's pi over 4, it's already decreased down to 0. So that means it starts off here, and it goes kind of down like this. So it decreases like that. And then between pi over 2 all the way up to 3 pi over 4, so once we get to 3 pi over 4, at 3 pi over 4, it's going to be back to 0. We're going to get r equals 0 again. But that's over here. So now it's back to 0. And then when we get up to, move this just a bit. There. When we get up to pi, now we're back to cosine 2 pi, so we're back to, we've gone one full, we've gone from 0 to 2 pi inside the argument of cosine. So now we're going to be back to root 2. So that's going to mean from 3 pi over 4 up to pi, it's going to increase back to root 2, which is going to be here. So it's going to go like this. Okay, now notice here that we're missing any piece between pi over 4 and 3 pi over 4. If we keep going past pi, what's going to happen is it's going to repeat this pattern of from root 2 to 0, and then nothing between pi over 4, 3 pi over 4, and then from 0 up to root 2 again, but it's going to do it in the region from pi to 2 pi. So we're going to end up getting a graph that's going to go this way. It's going to go like this. And then once we get to this would be 7 pi over 4, it's going to go back like this. So it ends up looking like this kind of infinity symbol. That's what the lemniscate looks like. And notice it's kind of part of, you could imagine it's like something that has these 4 leaves, except we don't have these other 2 leaves to it because we get the negatives underneath. So we just get these 2 here. And if we do minus the square root, so what you'll see is if you do minus as you go around from, say, 0 to pi, you'll just end up with the same graph. It'll just be traced out a different way. So this is the graph that we're looking at. Now, what's the region then? Well, it says in the first and the fourth quadrants outside the unit circle and inside this lemniscate. So that's got to be this little region right here. So that's the one we're looking at. So now to figure out the limits here, we need to figure out where these two meet, because we need to know what is this value of theta there, and what's the value of theta there, where they intersect. So that means we need to solve a little system of equations, so let's go ahead and do that. So we need to see, when does r squared equal 2 cosine 2 theta, when does that intersect r equals 1? Well, if r is equal to 1, then r squared also has to equal to 1. So we're really just solving when is 2 cosine 2 theta equal to 1. That means we need to know when is cosine 2 theta equal to a half. And that's going to happen when 2 theta is equal to pi over 3. Pi over 3. We get pi over 6. Now actually it's when theta is equal to plus minus pi over 3, right? Because it's positive pi over 3 or negative pi over 3. So this is really plus minus. So those are the two values of theta where these two intersect. Okay, there's pi over 6 minus pi over 6. Okay, great. So let's partition this off so we don't run into our own work. And what I'm going to do now is we're going to set up the integral. So we have to set up two integrals. The first one we need to integrate r squared. The other one we're going to integrate 1. So let's start with the r squared. So we need the integral of r squared dA. So this is going to be the integral from theta goes from minus pi over 6 to pi over 6. And r goes from, r goes from 1 up to square root 2 cosine 2 theta. And we're integrating r squared times r dr d theta. Now, of course, r squared times r is r cubed. So we're going to end up evaluating r to the 4th over 4. And may seem like that's going to be kind of tricky, but because of the square root, but because we're raising it to the 4th power, we're actually not going to get any square roots when we get our function to integrate with respect to theta. So let's go ahead and do that. So it's the integral from minus pi over 6 to pi over 6 of r to the 4th over 4 evaluated between 1 and square root 2 cosine 2 theta, d theta. I'm going to take the 1/4 out, minus pi over 6 to pi over 6. Now the square root, when I raise it to the 4th, it's just going to be what's under the radical squared. So it's going to be 4 cosine squared of 2 theta. Then I have to subtract off 1, so minus 1. And that's what I'm integrating d theta. Now, whenever you get one of these integrals from, say, minus pi over 6 to pi over 6, or minus 1 to 1, anything that's minus a to a, always do check, see if you can make your life easier, check if the function you're integrating is even or odd. This function here is even. You can check that. Cosine's an even function. So that means that I can just integrate, excuse me, I can integrate from 0 to pi over 6 as long as I double the value of the integral. It's one of the properties of even and odd functions. So if I double it, instead of getting 1/4, I really have a factor of 1/2, and I integrate from 0 to pi over 6 of 4 cosine squared 2 theta minus 1. All right, and now I'm just about there because I can integrate this. Let's see, this is going to be 1/2. Okay, so we need to use a trig identity here. This is going to be from 0 to pi over 6. Cosine squared of 2 theta would be 1 plus cosine 4 theta all over 2. So it's going to knock the factor of 4 down to 2, and we're going to get 2 times 1 plus cosine 4 theta, still minus 1. Okay, so all of this d theta. We're just about there, promise. I can do just a little more simplifying. If I distribute the 2, I've got 2 minus 1. So I end up integrating 1 plus 2 cosine 4 theta And now I can do the integration. This is 1/2. I'm evaluating theta plus, so it's 2 sine of 4 theta over 4, so that's going to leave a factor of 2 on the bottom. So theta plus a sine of 4 theta over 2. And this is all between 0 and pi over 6. All right, 0 contributes nothing, so I'm really just evaluating it at pi over 6. So that's going to give me 1/2 pi over 6 plus, looks like it's going to be 1/2 sine of 2 pi over 3. Okay, so that's pi over 12 plus 1/4 times the sine of 2 pi over 3 is root 3 over 2. So that's, let's get a common denominator here of 24. 2 pi plus, I need to multiply 8 by 3, so 3 root 3. Okay, so let's just keep this in mind. I'm not going to circle it or anything, but that 2 pi plus 3 root 3 all over 24, that's the double integral of r squared. So that's the total squared distance over this whole region. But we wanted the average squared distance. So we need to evaluate another integral. We need to evaluate the double integral of 1 dA. So we're just going to do the exact same integral, except instead of integrating r cubed, we're just integrating r. So 1 square root 2 r dr d theta. Okay, so this is going to follow very similar to the previous one, just a little different. So minus pi over 6 to pi over 6. Again, so this is r squared over 2. But again, it's an even power, so that's going to work out nicely with the square root. D theta. Okay, so that gives us, I'm going to take out the 1/2. And what are we left with here? 2 cosine 2 theta, subtract 1. Okay, so we are just about there. Let's see, this is going to be, again, notice this is an even function. Always be on the lookout for these things. Even function means I can double it, which means the 1/2 is going to become 2. Sorry, the 1/2 is going to become 1. So I'm just integrating from 0 to pi over 6. 2 cosine 2 theta minus 1. Okay, so this is going to be sine 2 theta minus theta. And this is from 0 to pi over 6. Again, 0 gives us nothing. So this is going to end up being the sine of pi over 3 minus pi over 6. Sine of pi over 3 minus a pi over 6. Sine of pi over 3 is root 3 over 2. So root 3 over 2 minus pi over 6. And let's get a common denominator, because we're going to have to be dividing this with what we got before. So it'd be 3 root 3 minus pi all over 6. Okay, so that's just the area. Now, through the average value, that means the average value, the average squared distance, is equal to the 2 pi plus 3 root 3 over 24 divided by this 3 root 3 minus pi over 6. So I'm dividing by it, so I'm going to multiply by the reciprocal. So times 6 over 3 root 3 minus pi. Now, of course, the 6 and 24 end up leaving a 4 in the bottom. Unfortunately, there's not really a whole lot I can do with the other stuff. You might think, well, maybe I can try and use a conjugate to do it, but it's got the square root 3 and the pi in it, so we really can just leave it as it is. So, our final answer, the average squared distance is 2 pi plus 3 root 3 all divided by 4 times 3 root 3 minus pi. And this is about equal to 1.397, which seems about right. If you think about the distance here, if you go up and look at the picture, the distance is going to be, a little bit bigger than 1, so it makes sense that the average square distance should be a little bit bigger than 1. So just a gut check on the approximate value there. So what we're going to do next is we're going to look at some applications of double integrals. So we're going to talk about centers of mass and moments and surface area, and then we're going to do triple integrals in 3 coordinate systems: rectangular, cylindrical, and spherical coordinates. And that will finish off this integration chapter. Then we just have one more chapter, which is the vector calculus after that.